Let's continue talking about volumes by slicing. So if you have a region in a plane that's revolved around a line in that plane, the resulting solid is called a solid of revolution. And we have a couple of pictures to show you down here. So first, let's look at this picture on the lower left side of the page over here. We have this plane region, this is the XY plane, and we want to revolve it around a line. And the line that we're going to revolve our picture around is the x-axis. So if I revolve it around this x-axis like this is just a little loop to show I'm revolving around this x-axis. Then it's like this orange curve gets rotated around, and you're going to end up with a three-dimensional object like we have on this picture on the right side over here. So this three-dimensional object is what we call a solid of revolution. Okay, so let me show you an example of calculating the volume of a solid of revolution in action. Let's take a look at example 2 over here. So when I take a look at example 2, we want to use the slicing method, which means we're going to look at cross-sectional areas to find the volume of the solid of revolution bounded by the graphs of this parabola, this vertical line, and this vertical line here. And we're going to rotate about the x-axis. So I think the first thing I'm going to do is I'm going to take my parabola y is equal to x squared minus 4x plus 5, and I'm going to complete the square. So the way that I complete the square is I leave the x squared there, the minus 4x there. I'm going to look at the coefficient in front of the x, this negative 4. And what I'm going to do is I'm going to take half of it, and I'm going to take half of that, and I'm going to square it. Okay? So half of negative 4 is negative 2. And what I'm going to do is going to take negative 2, I'm going to square that. Now, you're not allowed to just add whatever you like to a expression without changing it. So what I'm going to do next is, since I added that number in, I'm going to subtract it away. And then I still had my plus 5 from before. So you can see what I've effectively done is I've effectively added 0. But the purpose of doing this is when I look at this piece right here, this piece right here always factors as a perfect square. So this is going to give me the following. You know, when I look at this section right here, that guy is going to factor into x minus 2 quantity squared. Okay? And then when I go to simplify the rest of this part is going to be 4, so it's going to be minus 4 plus 5. That's going to give me a plus 1. Okay? So the reason why I completed the square here is then it can tell me what the vertex of the parabola is. So I'll say, therefore, we have a parabola with vertex 2, 1. So that's just going to help me graph the parabola a little bit. So let me sketch a graph over here. Here's a y-axis. Here's an x-axis. Here is 1, 2, 3, 4, and I'm going to label my point here's 2, 1. So when I go to graph this curve, I get a parabola that just kind of opens up like this. It opens up like this, it opens up like this. I don't know the exact shape. I'm just trying to draw a rough sketch to help you get the right idea. And we have x equal to 1 here. It's x equal to 1. This is x equal to 4. Maybe I should label my curve. This is y is equal to f of x. Okay. And I always want to label my axis of rotation. So in this case, I'm rotating about the x-axis. So my loop looks like this. All right. So if I were to shade in the area that we're talking about this shaded area right here in yellow. And we're rotating this about the x-axis. Okay, cool. Let's set up our volume integral. So our volume is going to be equal to an integral where we look at the cross-sectional area. And we're going to do everything in terms of the independent variable x. So we're going to look at the cross area with respect to x. And I need to know what my x values are ranging from. So when I look at my picture over here and I look at this shaded region, the x values range from 1 to 4. So I'm going to put a 1 over here. I'm going to put a 4 over here, like that. Okay. Then what I'm going to do is I'm going to chop up this. I'm going to chop up this picture vertically. And when I chop up this picture vertically, let me use a green pen to do that. What you're going to see is that I'm going to have a little bit of thickness between each of these green slices. That little bit of thickness is playing the role of the dx. So the dx is this little bit of thickness right here. Okay. And then I need a formula for the cross section of the area. Now, because I'm doing a solid of revolution, my cross-sectional area, this will be the area of a circle. And we know that the area of a circle is equal to pi times the radius squared. Okay. So what I want to do is, well, let me write an extra step here. So this is going to be equal to the integral from 1 to 4 pi times whatever the radius is squared dx. Now, when we look at this picture, I hope you guys can see, like for this particular slice right here, the radius of my circle is coming around the x-axis like this. The radius of my circle is just going to be the height of the function. So really, I can replace the radius with the integral from 1 to 4 pi times the function f of x squared dx. Okay. And I have a formula for what my function is. They told me that my function f of x was equal to x squared minus 4x plus 5. So really, this guy becomes the integral from 1 to 4 pi times x squared minus 4x plus 5 quantity squared dx. Okay. And really, this is how I'd calculate the volume. So I think I'll just end it right here, and I'll just mention, all you need to do is multiply out, find antiderivative, and plug in the endpoints. Okay, so this is how we're going to do this volume of a solid of revolution. So in the next couple of videos, what we're going to do is we're going to basically break these things down into two categories. So one category we're going to have something called the disk method. And the other method we're going to have is we're going to call it the washer method. The big difference between these two would be when you look at the disk method, your cross-sectional area is going to be a solid disk. So, it might look like a coin or something. It's a solid disk. Whereas with the washer method, we're going to have a hole in the middle. So there's one circle, and then there's another circle, but that circle has like a little hole in the middle like that. And how do you know if you're going to have a hole or not? Well, if you look at our picture on the left, over here we had a curve, and then the whole area went all the way to the x-axis. But what we're going to do is we are going to Um, maybe we'll have another line like this. If I have another line like that, then I hope you can imagine when we rotate about the x-axis, there's going to be a giant hole in the middle over here. So if we had a hole in the middle, then if our picture looks like this, when we have a giant hole in the middle, then the cross-sectional area is going to have a hole in the middle. And that's going to be how we get our washer. That washer would have a little bit of thickness like that. Okay, so this is what we're going to talk about in the next couple of videos. All right, everyone, take care.